This video is part of Unit 13, Properties of Solutions. We're still in Lesson 13.2, and this video is 13.3, and we will be covering solids. So let's go ahead and advance to number 5 and talk about solids. Up until this point, you've been told that solids are substances which have a fixed volume and a fixed shape. But we can further divide solids into two categories based on the way the particles are arranged. There are actually two kinds of solids. There are true solids, which are called crystalline solids, which we just call crystals, and amorphous solids. So we're going to start to talk about solids as having a fixed volume, but we'll look at the pattern. Now, only crystalline solids have a fixed pattern. This means the particles are arranged in some type of geometric pattern, and this is supposed to be a little more even, and that's what we've been calling solids all along. Because of this fixed pattern, solids have very sharp, distinct melting points. This is an intrinsic property. If you will recall, intrinsic properties are those that the size doesn't matter or the mass doesn't matter. For instance, the melting point of ice, 0 degrees Celsius, is the same whether you've got 1 gram of ice or a ton of ice. It's an intrinsic property. Here's another example. Sodium chloride is a crystalline solid. It melts at exactly 801 degrees Celsius. Now we'll consider another category of solids. They still have a fixed volume and fixed shape, but the pattern of the particles is random. It's not a particular geometric shape like you see in crystalline solids, and these are called amorphous solids. The property of amorphous solids is they melt over a range of temperatures. You don't have a distinct sharp melting point like you do with crystalline solids. Consider glass, butter, plastic. These are all amorphous solids. And just think about this. You've seen them melt or liquefy, so you know first they'll get soft, and then they'll get molten, and finally they can be liquefied, but there's no sharp melting point for amorphous solids. Amorphous solids have no pattern at all, so the particle arrangement looks just like a liquid. The only difference is they're frozen or in a fixed position, so they can't move out of position. Because of this, we describe amorphous solids as supercooled liquids. We don't further categorize amorphous solids, but we do further categorize crystalline solids. So let's advance the page to number 10 and 11, and let's look at these four types of crystalline solids. First, you have metallic crystals. Then you have ionic crystals. Then you have molecular crystals. And last, we have what's called covalent network crystals. We'll consider each of these in turn. First, let's take a look at metallic crystals. You've already seen this. We call it the electron sea theory. And this basically says that you have a large arrangement of positive ions with negative electrons freely moving between those ions. Metals do have a crystal pattern. They're a true crystal, so these will represent the metallic ions, and then we'll put the electrons in between, and I'll use these small red dots to represent the electrons, and this is the electron C. This explains why our metals are such good conductors of both electricity and heat, because these electrons flow freely between the atoms and carry the energy. So think about some of your classic metals. For instance, let's say copper and silver and zinc and chromium. We explain the properties of classic metals like this with the electron sea theory. It is a crystal pattern, but you have electrons free flowing. Let's advance to number 12 and take a look at ionic crystals. Once again, you've already seen ionic crystals because these are your classic ionic compounds such as calcium chloride and lithium bromide and so on. Here we have a pattern of positive and negative ions. This is a very strong ionic bond characterized by a distinct high melting point. And I'll draw a pattern here. These will be the positive ions, let's say, and then in between them will be the negative ions, and this is a classic fixed pattern and shape of positive and negative ions. Remember, the positive ions are called cations, the negative ions are called anions, and this pattern is called a crystal lattice. Ionic compounds, as I've just stated, are characterized by high melting points because this ionic bond is so strong. Next, we'll come to molecular crystals. These are molecular structures. These are molecules, or they could be single atoms. Now, what holds them together are these intermolecular forces we've previously discussed. Water is an example. Let's draw some water molecules. Now, within the water molecule itself, you have a covalent bond which is very strong, but the molecular crystal is created because you have these intermolecular forces. In this case, it's going to be hydrogen bonding that's holding these water molecules together. So, ice is in fact a crystalline solid, and it does have a fixed pattern, but the pattern is weaker than the other ones. Or the bonding is, the forces rather that hold the particles together is weaker than the others because it's just intermolecular forces. Let's look at some other examples. Oxygen. It's an element, but it's also a molecule. It's nonpolar, so dispersion forces hold these particles together, and that's why it's a gas. Bromine, another element which is also a molecule. Remember, these are the Hinkelbroths. It also has dispersion forces because it's nonpolar. However, because its molar mass is greater, it's a liquid. And then let's consider sulfur. S8, it's an element, and it's also a molecule. It has dispersion forces, but because its molecular weight is so big, it's in fact a solid. What characterizes these, though, is they all have very low melting points. That's because these intermolecular forces are relatively weak compared to metallic bonding, or the metallic crystal and the ionic crystal. And last we have the network crystal, where we'll find two examples will be graphite and diamond. The network crystal is in fact the strongest of the four crystal structures when you consider diamonds the hardest substance we know. It's still a lattice, it's a crystalline structure, but what happens is, because all the atoms within a network or molecules in a network crystal are connected together, it actually turns into what appears to be one large molecule. That's the network. So let's compare graphite and diamond. They're both pure carbon, but the difference in the hardness of graphite and diamond is the way those carbons are connected. Graphite is held together by dispersion forces. And what happens is, graphite is actually layers. Each layer is a series of carbon atoms which are held together in a network, but the layers themselves are connected by dispersion forces. So what happens with graphite is, it actually comes apart in sheets, and this is essentially the way a pencil works. The graphite, which we call lead, comes off in sheets. So it's a relatively weak force holding it together. That's why lead is so, or pencil lead is so soft. On the other hand, let's take a look at carbon in a diamond. Now, this is not a literal pattern. I'm going to do this just to illustrate a point. All these carbon atoms are connected in a network. They're connected to each other And that's what makes diamond so strong. This network crystal, it behaves as if it's one large molecule, and that's why diamond is the hardest substance we know. Another example would be silicon dioxide, which is quartz. On the Mohs hardness scale, that would be a 9, just one step below diamond, but it's the network crystal that also makes it very hard. And that brings us to the end of video 13.3. Now go to Moodle and answer questions 13.2 to go with these two videos.